Imagine standing on Mars at sunrise, where frost glitters in the half-light and the air is so thin that pure liquid water would not last. It would freeze, boil, or evaporate almost immediately, and yet this is the mystery that refuses to die. Does liquid water still exist on Mars today? For decades, that question has haunted planetary science because water is never just water. It is geology in motion, chemistry with memory. And for us, the one ingredient so deeply tied to life that whenever we find even a hint of it, the entire planet changes meaning. Mars, the cold red desert next door, once had rivers, lakes, and perhaps even vast standing bodies of water more than 3 billion years ago. That much is strongly supported by the geology, but the present-day Mars is another world entirely, and the challenge is not proving that water was there. The challenge is asking whether any of it is still liquid now. That mystery matters because modern liquid water would mean Mars is not just a fossil of a wetter past. It would mean Mars is still active in ways we're only beginning to understand. The problem starts with the Martian environment itself. Surface pressure averages only about 6 to 7 millibars, and the planet is intensely cold, with average equatorial temperatures around -50 degrees Celsius. Under those conditions, pure liquid water is simply not stable on the surface. So if liquid water exists on Mars today, scientists do not expect blue ponds, flowing streams, or rain. They expect something far stranger and far less cinematic. They expect brines, salty liquids whose dissolved minerals lower the freezing point and allow water to remain liquid at temperatures that would lock ordinary water into ice. On Earth, we spread salt on icy roads for exactly that reason. On Mars, salts could turn an impossible liquid into a fleeting one. And Mars has salts. Perchlorates, discovered by the Phoenix mission and thought to be widespread, are especially important because some of them can remain liquid at very low temperatures. Calcium perchlorate is one of the leading candidates because its eutectic temperature is around -75 degrees Celsius, low enough to overlap with real Martian conditions. That sounds promising, but Mars is cruelly selective. The same planet that can be cold enough for brines can also be too dry for them to form. Mars often gives with one hand and takes away with the other. Scientists describe this as a temperature and humidity conundrum. When Mars is warm enough, it is usually too dry. When it is humid enough, it is usually too cold. So the possibility of present-day liquid water shrinks to narrow windows in place and time. The search has unfolded like a detective story across orbiters, landers, rovers, and seismic instruments. Each mission has added a clue, and nearly every clue has come with an argument attached. One of the earliest tantalizing hints came from NASA's Phoenix lander in 2008. Phoenix touched down in the northern polar plains and found a landscape rich in ice and salts, exactly the kind of environment where brines might form. Then came the images that stirred the imagination. Tiny globules appeared on one of Phoenix's lander struts, and some researchers argued they behaved in ways consistent with liquid droplets interacting with perchlorate-rich material. Phoenix also measured abrupt changes in temperature and humidity, and other instrument data were interpreted as consistent with thin films or droplets of salty liquid in the shallow subsurface. But this was always treated as possible evidence, not a definitive detection. So Phoenix gave Mars researchers something invaluable and frustrating at the same time. It showed that present-day liquid water was not absurd. It did not show that the case was closed. Then curiosity entered the story inside Gale Crater. Using environmental measurements and neutron data, researchers examined whether calcium perchlorate brines could be stable near the surface or just below it. Those studies suggested that under certain conditions, especially at night and at shallow depths, calcium perchlorate brines might briefly be stable. Some analyses even proposed that deeper layers could preserve stable hydrated salts over longer periods. But again, the details grew more cautious as the data improved. Later work recalculating humidity conditions found that opportunities for brine formation were more exceptional than earlier estimates suggested. So the narrative kept narrowing. Not no water, but less water. Not obvious pools, but microscopic films, thin droplets or highly localized salty patches. And then there were the dark streaks. Few Martian features have inspired as much excitement as recurring slope linii, narrow dark streaks that appear seasonally on steep slopes and fade later. At first, many scientists thought these streaks might be flowing briny water. They seemed to lengthen during warmer seasons, and early spectral interpretations hinted at hydrated salts. For a while, these slopes looked like some of the best places on Mars to find active liquid water. But Mars is a master of false leads. Later analyses increasingly challenged the wet interpretation, arguing that dry, granular flows, dust movement, and sand processes explained the streaks better. NASA itself highlighted that seasonal dark streaks are a better fit to dry flow processes in many cases, rather than the ground being darkened by seeping water. A 2025 study using machine learning on a large dataset of streak features also favored dry mechanisms linked to wind and dust, not liquid water. That shift mattered deeply. One of the most visually seductive signs of modern Martian water started to look less like a current and more like an illusion. Yet even here, the story did not end cleanly. Some researchers still note that tiny amounts of brine might help trigger movement without creating visible streams themselves. In that view, water would not be the main sculptor of the streaks, only the hidden finger that nudges the dust. Meanwhile, another mystery emerged far below the surface. In 2018, radar data from ESA's Mars Express suggested a highly reflective region beneath the South Polar ice cap. The idea was electrifying. Interpreted by some as a subglacial lake of liquid water, it sounded almost like a planetary echo of Antarctica, a place where liquid water might persist in darkness and isolation. But the excitement came with a problem that scientists could not ignore. To keep water liquid that far beneath such cold ice would likely require extreme salinity and very specific conditions. As newer studies pushed harder on the data, the lake interpretation weakened. Enhanced radar observations reported by NASA in 2025 found that the bright reflection expected from liquid water was faint or absent in key observations, making the underground lake hypothesis much harder to support. So once again, Mars seemed to step back just as we leaned in. Another apparent pool of present-day water became less certain. Perhaps not a lake at all, but an unusual radar signature from rock, dust, or ice structure. And then came one of the most intriguing developments of all. Not on the surface, not just below the soil, but deep in the crust. In 2024, a PNAS study used seismic and gravity data from NASA's InSight mission to argue that fractured igneous rocks between about 11.5 and 20 kilometers deep beneath the landing site are best explained by liquid water saturating the pores. This was not a claim about puddles you could walk to. It was a claim about an underground realm, a hidden reservoir locked inside rock, far beyond the reach of current drills and rovers. The authors went further. If the InSight site is representative, they argued that the Martian mid-crust could hold an enormous amount of water, potentially equivalent to a global layer 1 to 2 kilometers deep. That is an astonishing thought. Not a wet surface world, but a planet that may have taken much of its ancient water underground and kept it there, out of sight for billions of years. But science is strongest when it argues with itself, and that is exactly what happened next. In 2025, another PNAS paper responded that the InSight results do not require a water-saturated mid-crust and provide only minimal constraints on actual crustal water content. In other words, the deep water interpretation is compelling, but it is not settled. The available data may be best explained by water in one model, yet they do not force that conclusion as the only viable answer. This is where the mystery becomes more subtle and in a way more beautiful. The answer to whether Mars has liquid water today may depend entirely on what we mean by have. If by liquid water we mean rivers, lakes, or wet ground, you could scoop with a shovel. The evidence says almost certainly no. Mars today is far too cold, too dry, and too low in pressure for persistent surface liquid water in any ordinary sense. If by liquid water we mean microscopic salty films that form briefly in rare conditions, then the answer becomes maybe. Not proven, but physically plausible in limited places and times, especially involving perchlorate brines. And if by liquid water we mean deep groundwater trapped in porous rock kilometers below the surface, then the answer might be yes, but with an important scientific asterisk. It is an evidence-supported hypothesis, not yet a confirmed planetary fact. That is the twist at the heart of Mars. The question sounds simple, almost childlike. Does Mars have liquid water today? But the real answer is layered like the planet itself. Mars may not be a world where water flows under open sky. It may be a world where liquid water survives only as chemistry on the edge, or as a deep memory hidden inside stone. And perhaps that is even more profound, because it means the story of Martian water did not simply end when the rivers vanished. It changed form. It retreated, concentrated, concealed itself, and turned the whole planet into a puzzle. For scientists, this changes how missions are designed. The best places to search may not be obvious canyons or streaked slopes, but carefully chosen environments where salts, ice, humidity, and temperature briefly overlap, or where geophysics can probe the crust below. For the search for life, the implications are equally careful. The 2024 Brines Review concludes that even if brines form on Mars, they would likely be tiny in amount, extremely salty, very cold, and highly uninhabitable by terrestrial standards. So the discovery of liquid water, if it comes, will not automatically mean Mars is alive. But it would mean Mars is still hydrologically active in some form, and that alone would reshape our understanding of the red planet. That is why this question keeps returning, mission after mission, paper after paper. Not because scientists want Mars to be wetter than it is, but because every hint of water is also a hint about climate history, habitability, and the fate of worlds. Mars is teaching us something larger than its own geology. It is teaching us that planets can hold on to their secrets by changing the scale of the answer. A sea can become frost. A river can become mineral. An ocean can become a whisper in the crust. So does Mars have liquid water today? The most honest answer is this. Probably not in any broad surface sense, possibly in fleeting salty micro-environments, and perhaps deep underground where our machines cannot yet reach. And somehow, that uncertainty does not make Mars less compelling. It makes it more human to us, a place where the biggest discoveries are not declarations but thresholds, where every answer opens a deeper chamber of questions. The next time you look at Mars in the night sky, remember that we are not just staring at a red dot. We are staring at a world that may still hide liquid water in forms so elusive that it takes orbiters, landers, rovers, and seismometers just to glimpse the possibility. And that is why we keep going back. Because somewhere between dust and salt, between frost and stone, Mars may still be holding a little water. And with it, one of the most intimate secrets a planet can keep. If this mystery pulled you in, stay with the journey because Mars is far from finished with us, and the next clue may already be on its way across the dark.